As engineers, we are given briefs by customers that must meet specific needs. So it's a big priority for making our wing. We must be able to hold 2.5 kilograms while having a max tip deflection of less than 50 millimeters and a max torsional compliance at the wing of less than 3 newtons per meter. We started the design process with conceptual design, defining the shape and structure of the wing to meet performance goals. This involved researching different structures such as these. We explored various spar structures with different joint methods and a range of shapes and sizes, as it was the most important aspect of the wing, providing strength. We had to make sure it would not collapse under our given load or due to torsion, so we started straight away testing some out with rough models. Eventually the spar broke near the clamp. This is because bending moment depends on the weight and its distance from the clamp, so the maximum stress occurs at the fixed point, which is why it breaks. Near the clamp it experiences compression on one side and tension on the other due to bending moment. The tensile side is more likely to fail because the material is weaker in tension than compression. We continued on to preliminary design, where we inputted known values and beam theory equations to predict if our spar would pass the requirements. By changing the dimensions of the spar cross-section, we could see at what width and height the spar should pass, using the second moment of area for bending resistance and the polar moment of area for torsion resistance. The equations and Excel sheet show that as we make the cross-sectional area bigger, it will become stronger and stiffer, however the weight will increase. Increasing the height and the top and bottom thickness reduces the amount of stress on the top and bottom, while increasing the width enhances the torsional resistance of the spar. After, it will show if our spar fits in the wing. We can then compare different cross-sectional designs for the spar, ensuring the spar can fit in the wing, altering location, rotation, or size, providing a visual representation as well. After creating a 3D design on SolidWorks of the spar using dimensions from our Excel, we then saw how it performed under a load of 24.525 newtons calculated in Excel. It confirmed that the stress was highest at the mounting point, and as distance increased, stress decreased. As we alter stress levels, we can see that the top and the bottom of the beam are the most stressed. Then gave us the idea of taking out more material from the spar at the end, to minimise mass which wasn't needed to support the wing. After simulating under torsion, we saw that it was along the middle of the spar's side where we encountered the maximum stress and torsion. So, we realised we couldn't take out too much material of the spar, as there would be a decrease in torsional strength and our wing would fail. In our final acceptance step, we began by laser cutting the ribs and opted to try and use minimal hot glue to avoid adding unnecessary weight. We fitted 8 ribs onto the prototype and marked a 10cm root extension with a masking tape. Although our wing exceeded the tip deflection with a point load of 24.525 newtons, it passed the torsional test. Moving forward, we plan to reduce mass by removing material from the spar end, adding movable flaps with tape, and modifying the spar shape to ensure it deflects less than 50 millimeters during the test.